So let us go over another example. In this example, we're going to roll a die. And our goal is to find the sample space and the events, and then try to find some probabilities. Very good. Example. The experiment is rolling a die. Okay, this is our experiment. I expect you to ask, what is the sample space? What is the collection of all possible outcomes? What is S? Well, it might be 1, right? Or 2, or 3, or 4, or 5, or 6. What we learned about cardinality or size of a set. Okay. The cardinality of set S is the number of members in that set. I write it as, well, cardinality of S, it only has 6 members, equals to 6. Okay. Consider the following events. I'm not going to list all of them. I'm just going over a couple of events. The first one is the event A rolling 1. B is rolling an even number. And C is rolling 7. Okay. So in this event, you only have 1 member. How many members are in the second event? And think about event C. Is it a possible event? So for event B, what do we have? We have 2 even number. It might be 2, it might be 4, or it might be 6, all right? What we can do with these events is to find the numerical characteristic for these events using the probability. Probability of an event is equal to. So for probability, the definition of a probability is that, first of all, probability is a function. But in the format that you're working with an event, it's going to be forming a fraction. On the numerator of your fraction, you're going to find the cardinality of your event. So what is the cardinality of the event that you're dealing with? And on the denominator, it's always the cardinality of your sample space. The cardinality of sample space. Okay. This is how we define the probability of an event. We form the event, we count how many members are in that event, goes on the numerator, then we already know the cardinality of the sample space, we put it on the denominator. So let's take a look at event A. What is the probability of event A? Okay. Probability of event A is equal to, we need to have a fraction. What's the cardinality of the first set? It only has 1 member. So you're going to write down 1 on the numerator. What's the cardinality of your sample space? Sample space has only 6 members. So 1, 6. The probability of event A is 1 over 6. What about the probability of event B? Probability of event B is equal to, on the numerator, you write down what is the cardinality or set or size of set B. It's obviously 3, 1, 2, and 3 members out of 6. So you can simplify this and you have half. And finally, the probability of the impossible event. It's impossible. The probability of C, the impossible event, is, well, we do not have any 7 in this sample space. So it's going to be 0.
What's the purpose of studying an impossible event if we already know it can't happen?
We need this 0.
Does the 0 come into play later on?
Oh yeah, of course, definitely, definitely. We're going to introduce the formula for the probability, and the general formula, we're going to use 0 in defining that formula for the probability. Yes, we need the impossible event. Think about it this way. In algebra, we say that, hey, we have the counting numbers starting at 1, then 2, then 3, then 4, then 5, and there are 7. What's the use of 0? Why we introduce 0? When you start subtracting these numbers, for example, 2 minus 2, even though 0 is not in this set, but 2 minus 0 must have a meaning. So we introduce something new. We say that, hey, let us call it 0 and expand this set into integers. There's always a reason that we need to define something like an impossible event. So here you have some negative numbers, some positive numbers, and the rest of them. In this experiment, we want to know what is probability of a blue candy. How do I find this probability? What should I do? What is your suggestion? You're the statistician and you want to know what is the probability that you randomly select one candy and that candy is blue. What should I do? Give me your suggestions. To find the probability for blue candy, we need a random sample. Random sample, okay. Let's take a random sample here. Let me change the focus of this. Okay, there. Very good. Opening up this and so how many candies do I need? What's the sample size? What's the cardinality of your sample?
Is that a value that we can choose?
Yes, of course, definitely.
20.
20, okay. I'm going to take these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18, and 20. So we have a sample of cardinality or size 20. Random sample, size of the sample is 20. Or the cardinality of sample is 20. Now, what's the probability of blue candy? What should I do now?
count how many blue candies there are in the sample?
Very good. It goes where?
Yes.
Goes on top.
Very good. How many? 1, 2 blue candies out of 20. So the probability is 1/10. So that's how we calculate the probability of different events. A question for you. So in this question, we have the following. You want to go and buy a car. So this is our experiment. Buying a car. So you have two options between Ford and, let's see, the other one is Honda. Between Ford and Honda. And each has two colors, blue and white. In how many ways? In how many ways? You can select a color. Okay. What if I add another option? Each one of these models have compact and mid-size. Mid-size. The same for the Honda. Compact and mid-size. Well, in how many different ways you can buy a car? Two different ways to select between the models, two different ways to select between the colors and being compact or mid-size. We have 8 different ways. Another example for you. In this example, the access code for a car's security system for a car security system consists of 4 digits. 4 digits. The information that we have is each digit can be any number between 0 to 9. Each digit can be any number between 0 to 9. So question says, how many access codes are possible if each digit can be repeated? Each digit can be repeated. So repetition allowed And each digit can be used only once. Each digit can be used only once. It means that no repetition. So what does the question says? Hey, you have 4 digits, right? 4 digits. So the first digit, the second digit, the third digit, and the fourth digit. It says you can choose between 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 options for each digit if it can be repeated. So 10 option, 10 option, 10, and 10. So what do you get? You get 10 times 10 times 10 times 10, or 10,000. You have 10,000 ways setting up the car's security system, access code. 10,000 ways to set the access code for the car. Well, part B says, hey, these digits cannot be repeated. For example, if you have selected 1 for the first digit, then you cannot select 1 for the second digit or third digit or the fourth digit. Okay, so let's see for the first digit, second digit, third, and fourth digit. How many options do I have for the first digit? I can select the first digit, 0, 1, 2, and 9. So I have 10 options for the first digit, but I cannot repeat that the digit that is selected for the first place. So I left with 9 options, then 8 options, and finally 7 options. So how many ways? 10 ways times 9 ways, 8 and 7 ways, which gives me, well, 50, 40. 40, 5,040 ways to set the access code with no repetition. Very well. Now let's talk about probability itself. Suppose you have sample space S. Let S be the sample space. What's a sample space? S is the collection of all possible outcomes. Suppose E is an event. Let E be an event. What's an event? Event E is a subset of S. Usually in mathematics, denote it this way. You say that, hey, E is a subset of S using the following symbol. Learn some set theory. So being a subset has the following symbol. It means that E is contained in S. Sorry. E is contained in S. So we can visualize this. to visualize this. Here you have set S, the larger set S. And then you have some subsets like E. Set E is contained in this larger set. It's a sub-collection or subsets. The probability of event E is a number which is sandwiched between 0 and 1. So the probability of event E is a number between 0 and 1 inclusive. So it can be, for example, a half. It can be, for example, a fifth. It might be like 0.15, 0.50, and the rest of these numbers. But it's not negative. Note that. Probability cannot be negative. It cannot be, for example, 2 point something. Probability cannot be 2.05. It cannot be like 1.001. It cannot be larger than 1 at all. At most, it's going to be 1, and at least it's going to be 0. Now let us go back to event E. This is your larger set, set S, and this is the smaller set, set E. We can define the complement of event E, which is going to be the rest of these members here. E complement, EC. So the complement of set E is denoted by, in different books, they use different symbols, different notations. Some of them write it down as E to the power C. Some books write it as E with a little bar on top of it. Some books write it as E with prime on top of it. And they say, hey, this is the complement of set E. Very well. So mathematically, we write it this way. Complement of set E is the set of all members in S that are not in E. The complement of set E. Now to move further, we're going to define the operations between sets. Very good. Operation between sets. Let A and B be two sets. We can define the union between A and B. A union B, denoted by A U. B is a new set. This set includes members in set A, in set B, with no repetition. the set of all members in A, in B, no repetition. Okay, very good. We can define the intersection between two sets, A, flip U, you get the intersection between A and B, which is defined as the set of all members that are in A and B at the same time. All common members in A and in B. And finally, the difference between two sets, A minus B. Okay. When we're talking about A minus B, we're talking about the elements, the members in set A that are not in set B. All members in A that are not in B. So these are the official definition coming from set theory. Give us an example. Okay, let's take a look at this example. Suppose set A is equal to 1, 2, 3, 4, and 5, and set B is equal to, well, suppose you have 5, 4, 6, and 7. We have two sets. We want to know what is the union between two sets is, what is their intersection, and what is the difference between them. The union, A union B says, hey, I am a new set. In this set, you're going to list all members without repetition. So what is in A? 1, 2, 3, 4, and 5. What is in B? 4 and 5. I already have 4 and 5. I already have one representative here. The rest is 6 and 7. What about the intersection? Intersection is the set of all common elements, repeated elements. As you can see, 4 and 5 are the members who are repeated in these two sets. And finally, the difference between these two sets, A minus B, is equal to all members in A that are not in B. 1 is in A. Is it in B? No. So I'm going to write it down. 2, I'm good with 2. 3 is in A, but not in B. 4 is not acceptable because 4 is in B as well, is a member in B. 5 is not acceptable, so A minus B has only 3 members. Very good. So let us continue. So far, we talked about the union, the intersection, we talked about the complement, we talked about the difference. What's the formula connecting all of these together? So the cardinality of A union B is equal to the cardinality of A plus cardinality of B minus the cardinality of A intersecting B. So this formula actually connects the cardinalities together. Why we need that? Remember, in the definition of probability of an event, on the numerator we had the cardinality of that event. So let us check to see if this formula satisfies the condition that we discussed for these two sets. What is the cardinality of A union B? The cardinality of A union B, 1, 2, 3, 4, 5, 6, 7, 7. It is 7 on the left-hand side. On the right-hand side, I have cardinality of A, 5 members, plus cardinality of B, 4 members, minus the cardinality of the intersection, which is 4 and 5 with 2 members. So here you get 7. 7 on the left is equal to 7 on the right. So this formula satisfies for this specific example and any other example that you can come up with. Check this formula for that example as well. The cardinality of the union of two sets is the cardinality of the first set plus the cardinality of the second set minus the cardinality of their intersection. Well, so now how to connect this formula to the probability definition? To the probability. Remember that. We said the probability of an event like E is equal to the cardinality of that event divided by the cardinality of your sample space. The definition of probability has connection with the cardinality. So, let me erase these numbers and write it down for you here. The probability of A union B is equal to the probability of event A plus the probability of event B minus the probability of A intersecting B. I'm representing a new formula for you. Where does it come from? It comes directly from the definition of probability. How? Prove it. Okay, let me prove that for you. Proof. The probability of A union B using the definition of probability is equal to, on the numerator, I have the cardinality of A union B. On the denominator, I have the cardinality of S. What is S? S is your sample space, whatever it is. But we know that the cardinality of A union B can be written as the cardinality of A plus cardinality of B minus cardinality of A intersecting B divided by the same denominator. Now what I'm going to do, I'm going to separate these one by one. This is just a fraction. I can take these numerators and start dividing by the same denominator that I have. What do I get? I get, well, the cardinality of A divided by cardinality of S plus the cardinality of B divided by the cardinality of S minus the cardinality of A intersecting B divided by the cardinality of S. But this is nothing but the definition of probability of event A. This is P of A plus P of B minus P of A intersecting B. We just proved this formula. Very good. So let's talk about two events that are disjoint. I'm going to erase this part of the board. And I'm going to just work with the same set. I'm going to change the second set, set B, into 6 and 7, or 7 and 8, 6 and 7. Okay, so in forming the union between these two sets, A union B, you know that you just list all the members, no repetition. So here you have 1, 2, 3, 4, 5, and 6 and 7. Okay, the cardinality of the union between A and B is equal to, well, 3, 6, and 7. What about the intersection between these two sets? What is A intersecting B? What are the common elements? What are the repeated elements? Well, we don't have any. So we're going to use the symbol for empty set, or you just write it as empty set. They have the same meaning. So what's the cardinality? How many members are in the intersection? A intersection B. How many members? None. So 0 members. When it's the case that there is no intersection between two sets, we see that those two sets are actually disjoint from each other. We say A and B are disjoint. So two sets are disjoint if their intersection is empty. Okay, very good. So let us go back to our probability. Probability formula says the probability of A union B is the probability of A plus probability of B minus the probability of their intersection. So the probability of A union B becomes, for two disjoint sets, P of A plus P of B minus the probability of the intersection is 0 divided by the cardinality of S, or 0. Very well. So for any disjoint events, the probability of their union is the probability of A plus probability of B. That's where we use the empty set, the probability of empty set to be 0, because we want to show that, hey, if you have disjoint events, disjoint sets, their probability is the sum of each of those events' probability. So I expect you to ask, you talked about the complement of a set. Is the set and its complement disjoint from each other? Question. Consider event E and its complement. Is E intersection EC is equal to empty? This is the question. Can I say that the probability of E intersection EC is 0? Putting a question mark on the board. So this example. Let's consider rolling a die. We learned that the sample space S is 1, 2, 3, 4, 5, and 6. I'm giving you this event, the event E, which is even numbers, rolling even numbers, 2, 4, and 6. What is the complement of E, EC? Well, based on the definition, it says, hey, all numbers that are not in E. Okay, it means that we are dealing with the odd numbers, 1, 3, and 5. So now E intersection EC. What are the common members, common elements? None. So it is equal to empty set. So the probability of E intersecting its complement is 0. It's not happening, never. You can think about S as your larger set, Venn diagram. This is my S, including 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And E is going to be this set, 2, 4, and 6. This is my E. The rest are the complement of E, EC. So as you can see, they have no intersection with each other. Very well. So what are you implying? I'm implying that, hey, I know for any two disjoint events, the probability of their union is the probability of the first set plus the probability of the second set. But what is the union between E and EC? E union EC. Okay, it means that I have to take all of the elements and write them down without repetition. 1, 2, 3, 4, 5, and 6. But isn't that the same as S? Yes, of course. The probability of E union EC is equal to the probability of S, which is equal to the cardinality of S divided by cardinality of S, which is equal to 1. Hey, now we can drive a new formula. The probability of E union EC is equal to the probability of E plus probability of EC, but this is just 1. So P of E plus the probability of its complement is always 1. New formula. So if you have the probability of E, we can easily calculate the probability of its complement, or if you have the probability of its complement, we can easily find the probability of E itself.